those are two different approaches.
Thank the organizers, and especially Aurora, for their invitation to give a talk in this nice workshop. The topic of my talk concerns the key reaction studies for S process in massive stars using transfer reactions. As you heard already many times this week, S process nuclear synthesis is responsible of half of the abundance of the heavy elements present in the universe, and the elements having mass between 60 and 90 are produced in massive stars through the so-called weak S process component. This process occurs during the core helium burning phase at this temperature and density, and partly during the shell carbon burning phase at higher temperature. And the neutrons needed here to trigger the S process are mainly provided by a neon-22 alpha reaction, as Andreas Best showed already yesterday. Here what I show is the result of a sensitivity study that was performed recently, where they investigated the impact of the nuclear incertaities, the N-gamma incertaities on N-gamma reactions on the abundance elements of the S elements produced in weak S process. And they found out that actually most of the elements have an uncertainty of about 30%, and only 10 N-gamma reactions really have a strong impact, leading to an uncertainty of more than a factor of 2 or 3 for these elements like krypton, selenium, and so on. But they showed also that actually the most important reactions that affect the S abundances with much larger uncertainties, sometimes order of magnitude, are neon-22 alpha and neon-22 alpha gamma reactions. And in the case of low metallicity rotating stars, oxygen-17 alpha and oxygen-17 alpha gamma have also strong impact. And actually in the following, I will first show the case of these two reactions that we studied recently. But first, I want to show you why they are important. Normally in metal-poor massive stars, the S process production is negligible due to the low neon-22 and the iron seed abundance. However, recent models of this metal-poor massive stars that introduced fast rotation showed that the induced mixing, strong mixing between the helium burning core and the hydrogen burning shell mixes up the primary carbon-12 and oxygen-16 into the hydrogen burning shell. And this leads to the production of additional nitrogen-14 through the cyano cycle. This nitrogen-14 then mixes back to the helium burning core and produces neon-22 through this chain of reactions. So this fast rotation produces, enhances the production of neon-22, which then through neon-22 alpha reaction release a large number of neutrons, which combined with the low iron seed leads to a large production of S elements between strontium and barium, contrary to the weak S process, to the standard weak S process, which produces elements up only to strontium. This called enhanced weak S process may have important impact on chemical enrichment in the early galaxies. It is maybe the source of the heavy elements such as barium in the early universe, and its production, coupled to the air process production, is maybe the explanation of the dispersion observed in the light neutron capture elements over the heavy neutron capture elements in the galactic halo stars. But before confirming these claims, one needs to know the final abundance of this weak enhanced S process, which actually depends strongly on the neutron poisoning effect of oxygen-16, which is determined by the oxygen-17 alpha and to oxygen-17 alpha gamma reaction ratio. And this is what is observed here. Actually, you see the neutrons that are absorbed by oxygen-16, they are either released in the medium through oxygen-17 alpha, which leads to the enhancement of the S process, or they are lost for good via oxygen-17 alpha gamma. And this is what you can see here. Here is the overproduction factors of this S element. In red is when using the oxygen-17 alpha gamma rate of Coglan and Fowler. And then when you divide this rate by a factor 2, you see an enhancement of the S element between strontium and barium by a large, very large factor. So a decrease of this oxygen-17 alpha gamma or an increase of oxygen-17 alpha has an impact on the neutron recycling efficiency. So what is the status of these two reactions? During the core helium burning temperatures, these rates are dominated by resonances in this energy range, which corresponds to these excitation energies here in the compound nucleus neon 21. And for shell carbon burning, which is at higher temperature, the resonances which contribute to reaction rate are these ones here that correspond to this excited state. Several oxygen-17 alpha and oxygen-17 alpha gamma direct measurements performed. For oxygen-17 alpha, and the older one was one of Andreas Danker, and the recently is the one of Andreas Best. And you can see that all these direct measurements were performed all at this excitation energy. Is there a problem here? Okay. Okay, the direct measurements correspond to these excitation energies here, and there are no direct measurements in this region of interest for helium core burning because they are very difficult to perform. And what about the spectroscopy of neon 21 in this region of interest? If you know the excitation energies, the spectroscopic factors, the alpha withers, neutron withers, and so on, then you can calculate the resonance strength and calculate the reaction rate. But unfortunately, for this state here of interest, the spectroscopy is poorly known. And actually, none of them has known alpha spectroscopic factor and so alpha width. And some of them have no spin parity assignment neither. So, a recent measurement of the neutron withers were obtained through a neutron transfer reaction that was performed at Tunnel. And the alpha spectroscopic factors of the states of interest were investigated for the first time by our collaboration using, the experiment was performed at MLL, Munich, the year it was closed, unfortunately. So neon 21 states were, oh, sorry. How can I come back? Okay. So neon 21 states were populated through oxygen-17, lithium-70 alpha transfer reaction. So a lithium-7 beam of 28 MeV was delivered by the 14 megawatt tandem of MLL, then sent on an oxide tungsten enriched target in oxygen-16 that was on carbon backing. And the emitted tritons were momentum analyzed by this high energy resolution spectrometer Q3D. And they were detected in the focal plane by two proportional gas counters and plastic scintillators, giving information about the magnetic rigidity of the particles, the energy losses, and so on. The angular distribution measurements were performed at different angles, ranging from 7.5 to 45 degrees in center of mass. And the angular distribution were performed not only on the enriched target, but also on the natural oxide tungsten target for calibration and background evaluation purpose. And here is one of the excitation energy spectrum that was measured at 9 degrees. So many states of in the region of interest were populated depending on the angle. They were populating at each angle, but they were not observed at each angle because of these huge oxygen-16 contaminants coming from the carbon-12 lithium-70 background. And these peaks have different kinematic angle dependence. So depending on the angle, you see some of the states of interest, and the other angles these two peaks were moving, and the states that are hidden here were showing up. So there are holes in the angular distributions. This is the experimental energy resolution that you obtained, something like 30 keV at low angles and 71 keV at 36 degrees. And because of this, this triplet here was treated as one component, and the same for this doublet here. To extract then the yield of each peak, fit of the whole spectrum was performed using multiple modified exponential Gaussians with common width and common exponential factor. And once the yields are extracted, then we normalize to number of atoms per centimeter square and solid angle, and so on. The angular or differential cross sections of these different states were extracted. And you see here the data together with the final range DWBA calculations that were performed using Fresco code. You see here that most of the data are well described by this DWBA model, which gives a strong evidence of the direct mechanism that's going on in this transfer reaction. So for this triplet here, as I said, it was treated as one component. So, but for the fit, it was fitted with three components. And two of the components, actually, the alpha spectroscopic factor was derived from the alpha width that was measured by Vestital through direct measurement. And then the alpha spectroscopic factor of the third component was determined from the present work, from the chi-square minimization of the three combined curves to the data. The same here for this doublet here, one of the components, the alpha spectroscopic of this component was derived from the alpha n measurements of talvaritar. And the spectroscopic factor of the other one was determined then from, again, the chi-square minimization of the combined curves. For these ones here, where you have only one state, I mean, it's more simpler, but you see here that for the 7.81 and 7.74, there are many curves because their spin parity are not known. So we performed calculations considering different alpha angular momenta, again, and going from 0 to 4. For this one, the curves that fit best the data and given reasonable chi-squares were this one here from L alpha equals 0 to L alpha equals 2. But in case of L alpha equals 0, the alpha spectroscopic obtained is quite large, and this is unlikely because of this high energy of this excited state, knowing that there are 5 states that are having 5 half-plus at low-lying energies. For the 7.74 MeV, the data could not discriminate between these 5 curves. I mean, they could not discriminate between the different alpha angular momenta. Once the alpha spectroscopic factors were determined, then the alpha widths were calculated using this expression where PL is the penetrability factor and phi R is the alpha plus oxygen 17 radial part of the wave function that was calculated at a radius where the wave function reaches its asymptotic behavior. And it was calculated using Fresco code also and loosely bound approximation. And the uncertainties that were obtained, part of them is due to statistics, depending on the states. When you have good statistics, the statistical error was quite small, but for this one, the statistical error was large. But the main uncertainty comes from the optical potential parameters. We performed, calculation with different entrance and exit potential parameters, and from there we deduced this uncertainty.
Sorry, but don't know any dependence on the wave function.
Yeah, this was, there is actually, that's an interesting question. There is a dependence on, but you see, the dependence that we found on the alpha spectroscopic factor was of about 30%, 25%. But actually, when you calculate the alpha width, you have also dependence here. And what we found, which is interesting, that the dependency was canceled. I mean, the error bar that we found on the alpha spectroscopic factor of 25% became much smaller than 6% on the alpha width. I mean, you do the calculation.
Sorry, what content was?
We do the calculation of the alpha spectroscopic factor, considering some radius and diffusivity for the wave function. And we do the same calculation with this and look how the alpha width is changing. The change that we saw in the alpha spectroscopic factor, there is also a change in this one. And surprisingly,
yeah, because they are the same thing.
Yes, exactly.
Okay.
And that was nice because the 25% uncertainty in the due to this binding wave function cancels and becomes smaller.
Without these two terms.
Yeah.
Anyway,
We are interested in the alpha width, so that's the nice thing. Okay. So once we determine then these alpha widths, we use them to perform the oxygen-17 alpha and oxygen-17 alpha gamma reaction rates calculations using the rate Monte Carlo code of Richard Langland. So for the energies below 721 keV and at this energy, which are of interest for helium core burning phase, so we used, of course, the present alpha widths that were determined for the first time experimentally. And for the states at higher energy than 721, we used the alpha widths and neutron widths coming from best etale direct measurement. For the neutron widths, we used the one coming from the neon 20 GP transfer reaction. And for the gammas, we used the width is coming from systematics of half-life measurements that were measured by Ross a long time ago. And for some state, we used constraint also using the, of course, the alpha gamma resonance strength of Matt Williams. It was also, that was performed in TRIUMPH. And here are the results. So in pink and red are the alpha N and alpha gamma reaction rates of best etale, NACRI, and Coghlan follower normalized to our median reaction rate here in black. And the black dashed lines are our low and high rates. So what do you see? You see that for oxygen-17 alpha N, our rate is much larger than the one of best etale by a factor of 20, and it's larger than the one of NACRI by a factor of 5. For the oxygen-17 alpha gamma, our rate is compatible with one of best etale within a factor of 2, and is smaller than the one of Coghlan follower by a factor of 5. And now if we look to the alpha N to alpha gamma rate ratio, you see that our result, which is here in black, is 20 times larger than the one of best and 30 times larger than NACRI to Coghlan follower that are used in S-process modeling of this low metallicity massive stars. So you see that with our reaction rates, we have a better neutron efficiency recycling than what was recommended before. But before showing the impact of this on the S elements, I would like to show you these figures, which represent the fractional resonant contribution of the different resonances to the total reaction rate. So you see here that for oxygen-17 alpha N, the states that really, the resonance states that contribute the most to the alpha N reaction rate are the 472 keV and 392 keV, which are actually the 7.82 and 7.74 MEVXI states in neon 21. And for oxygen-17 alpha gamma, it's again the 472 keV and the 308 keV, which contributes most in the, for the helium core burning temperature, which is between 0.2 and 0.3. But as I said before, the 7.74 and 7.82, have no known spin parities. And from our measurement, we could not constrain the alpha angular momenta of the 7.74. And we found 3 possibilities for the 7.82, even if the best chi-square was obtained for L alpha equal 1. So these are key resonances that need to be measured. Their spin parity need to be measured in the future. Nevertheless, we performed the reaction rate calculations by considering the worst case. For the 7.82, we performed the calculation considering L alpha equal to, and no contribution at all for the 7.74, which corresponds to an alpha angular momentum larger than 3. And these were the results. Even in this extreme case, in this worst case, the alpha into alpha gamma rate ratio that we calculate is still 20 times larger than is 20 times larger than Nacli to Cogram 4 rate. It is 10 times larger than the one of Bestar. So even with this extreme case, there is the neutron efficiency recycling is better than what was before. I just want to mention that Bestar in his calculation considered an L alpha equal 0 for the 7.81 and for the 7.74. You can confirm. Okay. And okay, now if we look to the effect, the impact of our reaction rate calculation on the S process in rotating pool metal massive stars. So once a nucleosynthesis calculation mimicking the core helium burning phase of low metallicity rotating massive stars of 25 solar mass was performed by Arthur Chopin. And here are the results. So these are the production factors of the S elements. In red is when using our rate, and within there is activities, and in black is when using Bestar rate. So you see really a large enhancement of more than 1.5 Decs between strontium and neodymium here. And the largest effect is actually observed for barium. See, 2 orders of magnitude enhancement in the production of barium. Okay, that's for oxygen 17 alpha and oxygen 17 alpha gamma. What about the 2 competing reactions, neon 22 alpha N and neon 22 alpha gamma reactions that Andreas talked about yesterday? So again, I mean, so already these pictures, neon 22 alpha N is the main neutron source for the weak S process in massive stars, but due to its negative Q value, this reaction is effective at nearly at the end of the core helium burning phase at these temperatures, while this reaction here, the competing reaction neon 22 alpha gamma, which has a positive Q value, is effective during the whole core helium burning phase, thus reducing the quantity of neon 22. And at these temperatures, the resonances that are important for the reaction rates are in this energy region, which correspond to this excited state in the compound nucleus magnesium 26. As Andreas showed yesterday, okay, there are many direct measurements that try to perform measurements down to the neutron threshold here, but unfortunately, because of the large background, the neutron detectors due to cosmic rays, they could only get upper limits in this region where there are many states in magnesium 26. So they could only measure really this resonance, which is important for the reaction rate. The same for neon 22 alpha gamma, they could only measure the resonance strength of this resonance. So many indirect measurements were performed also to try to clarify the situation, to improve the situation. So there are many scattering and N-gamma reactions that were performed, and from where the neutron withers, gamma withers, and spin parities were determined, and there were transfer reaction measurements, and I will talk about this part. So the first alpha transfer reaction measurement that was performed to study these 2 reactions is the one of Gisen using lithium 6D alpha transfer reaction and the neon 22 gas target. And this was the excitation energy spectrum they obtained. So you see here the resonance, the state which corresponds to the resonance that was measured in the direct measurement, the 11.31 MeV. You see this one, but the energy resolution was poor. something like 120 kV due to the Havard windows. So they couldn't really discriminate the states that are populated here, and they had a large background here. Then Ugaldi et al. Performed another lithium-6D experiment, but this time with an implanted neon 22 target implanted into 40 microgram centimeters square of carbon. But unfortunately, as you can see here, they saw a lot of background. I mean, they saw only these two states, not even the 11.31 MeV. And I mean, the other states were hidden below this contamination coming from the carbon backing. Then more recently, there was the experiment of talvaritar that was performed in Osaka through lithium-6D transfer reaction using neon 22 gas target and the high energy resolution spectrometer radon. The energy resolution they got was of about 100 kV. But at this high energy, the momentum matching is quite poor, knowing that the states that we are interested in are more the 0 plus, 1 minus, 2 plus. So, okay. And this is the excitation energy spectrum they obtained. So they saw the 11.32 MeV, this ones, and the 11.17 MeV. This was the first time that this state was observed in these transfer reactions. And here are the angular distribution measurements. They performed only measurements at 2 angles. And here they could only extract like upper limits. So for the 11.31 and the potentially important 11.17, yeah, actually here they have only upper limits. And as you can see, the data are consistent here for this one, for 11.17, consistent with 0 plus, 1 minus, 2 plus. For this one, it's consistent with 1 minus, 2 plus. In my opinion, angular distributions with only, transfer reactions at only 2 angles isn't the best to do, because it depends about the reaction mechanism that you can have. We need to measure at larger angles to know exactly if you have only direct transfer of if there is compound nucleus mechanism going on or a multi-step process. And then there was an experiment at Texas A&M using it's an IMC measurement. Here, this time, they performed the transfer reaction in inverse kinematics, where they sent a neon 22 beam onto a lithium-6 target, and they performed also neon 22 lithium-70 transfer reaction in inverse kinematics. It was performed at sub-Coulomb energies. I think the energy of the beam was of about 1 MeV per nucleon. And they used the multiple dipole multiple spectrometer of Texas A&M that was at 5 degrees to measure this excitation to populate the states of interest. Here again, they populated the 11.31, but no hint of the 11.17 MeV. The one that was observed in Osaka experiment disappeared here, but they saw a state at 11.08 and these 2 ones here that were observed here also. Here, they got a quite very good energy resolution of about 95 kV. This was the best for the moment for this neon 22 lithium-60 and lithium-70 transfer reaction. And actually, in this measurement, in both reactions, they didn't see this 11.17 MeV. Then the story continues, and there was the experiment of Otta et al. Again at Texas A&M. Okay, I'm nearly finished. Is it for me? Okay. Okay. The experiment was performed at 7 MeV per nucleon, which corresponds to 42 MeV total energy. It's again in inverse kinematics. They measured the deuterons using the Tiara silicon detectors. And in coincidence, they measured the gammas in germanium detectors and the recoils using the MDM spectrometer. But the energy resolution here was really bad, between 200 to 250 kV. And this was the spectrum they obtained. So they see the 11.31, then a bump here, where they identify the state thanks to the gamma ray measurements. They identified also something which corresponds maybe to 11.17, but not all the gamma ray transitions of all the cascades were measured. So was it really the 11.17 MV? Not sure. Anyway, here also the angular distribution measurements were performed at only 3 angles, and this is the 11.32 MeV. In that case, the data are consistent with the 0 plus and 1 minus, while in Osaka it was consistent with 1 minus 2 plus. We can say that if you combine both, it is maybe consistent with 1 minus. And here is just a summary of the magnesium-26 spectroscopy situation coming from this recent transfer reaction measurements. So as you can see, it's quite a mess. For the 11.17 MeV, yeah, that was observed in talvaritar. You have this alpha with us, while in Jayatissa, they gave these upper limits, which are order of magnitude smaller than what was observed in Osaka. And for Ota, its upper limit was also smaller than this one by a factor, yeah, maybe more than 2. For this one here that was observed only in Jayatissa, their value is yes, 1 order magnitude larger than the upper limit that was found in Talwa. They agree for this one. They agree within a factor 2 for this one. And for this one, Talwar and Ota agree also within a factor 2, but their value is larger than the one obtained in the INC experiment. So this situation, I mean, this table is just telling you that there is a need for more indirect studies of the key resonances, and of course, a direct alpha and alpha gamma measurement with less background, like what is planned in Luna, or by performing here also measurements in EVA schematics with the recursive spectrometer separator like Dragon. And in our lab, we are planning to perform neon, to populate the magnesium-26 through the neon-22 lithium-70 alpha transfer reaction measurement at the Alto facility. And the idea here is to perform angular distribution measurements at least at 9 angles between 3 to 40 degrees in center of mass. And we are aiming to perform measurements with the 2 types of targets, neon-22 gas targets, but this time the windows will be made by nickel. We did some tests with the nickel windows and the background is really very low, but to have a good energy resolution, I mean, less than 100 kV, you need this thickness, which is quite challenging to obtain without holes in the foils. And we are planning also to do measurements with the implanted neon-22 target, but with more area density than in Ugadi experiment. And this time the implanted neon-22 will be on a nickel backing to avoid this carbon background. But for this kind of implanted target, there is always the question of stability under the beam. And of course, this needs to be monitored with a silicon detector. And the experiment will be performed, let's hope, next year using the split pulse spectrometer. So rendezvous in 2-3 years. And let's see if this experiment will clarify the situation or add entropy to entropy. We will see. And I just want to tell you thanks. And these are the people that participate to oxygen lithium-70 experiment in Munich. It was a very fun experiment. And actually, most of these people will participate to neon-22 lithium-70 experiment in Oxford also. Thank you.
Thank you, Ferouz, for also being on time. So let's open the session for a couple of questions.
Just one question, not really a question, a comment about these neon implanted targets. So with the group in Seville, we have tested helium adsorbed targets on silicon. And we tested them with heavy ions in Catania. It was very like nickel, so it was tandem meet between nickel that is lost, and they showed very good stability.
They were stable?
Yeah. We also carried out a bunch of experiments, but with radioactive ion beams. So of course, in that case, the rate was much lower than we got at our tandem in Catania. I don't know the chemistry of neon 22 in silicon. So, but
yeah, I don't know. I think we will ask them to see it.
It's a bit different. It's not implanted. It's they kind of grown in let's say an atmosphere.
Yeah, I visited actually the place. They show it. Yeah. At Legnaro. No, not at Legnaro. At in Sevilla. Yeah, I think we will see. We will look also to this option. I mean, all options we are open for all options.
I have produced and used implanted neon 22 target in the past
backing?
On tantalum in Legnaro. There's a small implanter, and but we have used them with the proton beam. The energy was up to 1.3 megavolt, and the intensity was around 10 microamperes. So I guess much higher current, but a lighter isotope and with lower energy. Yeah,
the energy will be 28 mV.
I know. So one should evaluate the dissipated power.
Yes.
We were cooling them with water throughout the data taking, but they performed pretty well.
So they were stable on the whole.
Very stable, yes. So we could run like a whole week with one target.
Okay. And the implanter is where?
In Legnaro.
In Legnaro, okay.
Yeah,
so we are aiming to do it. We have an implanter also in Orsay.
Okay.
Yeah.
And the profile also turned out to be, I mean, we we decided the implantation energies and doses using SRIM and predicting the profile. And in the end, what turned out, I mean, they turned out to be very close to the predicted profile. So yeah, they worked pretty well. And yeah, if you need some contacts, we can
I will
talk.
Discuss with you later.
Yeah, okay.
Thank you.
Okay, thanks. Aurora, you had some other? Okay.
They had some experience for neon 22 targets. That's it.
So, yes, ladies first. So, Ariana.
Thanks. How are you dealing with the nickel foils?
With the nickel what?
Foils for the entrance, because we are using it in Felsenkeller with 1 micron and it's not light tight. So this 0.5 seems to me even...
That's the reason why I say it's challenging. Actually, because first of all, we were trying to find that at Goodfellow they have this nickel foil, this thickness, but the problem, they have holes. But now what we will do, and this is the test we are working on, is our target maker will evaporate nickel.
Okay.
And we will make the nickel we are not buying faults. We will evaporate the nickel, trying to make this.
Okay, because we were thinking about another solution by taking this 2.5 micron that they sell as a light type and then etching.
Laminate.
Yeah.
This term exists in English. Laminate. Yeah, this also. I mean, we are looking to all the options. Yes.
So just back to the option 17, the alpha gamma can probably relatively easily be measured at Caspar or at Luna, for example, at Luna MV, that is. But does it make sense since you showed that it seems to be so low and the ratio alpha n to alpha gamma seems to be so high that maybe it's impossible to get any kind of neutron suppression through that?
This is what I show exactly that. Yes, I don't know. It's always nice to have other measurements with different methods to to check that everything is consistent, I would say. But yes, oxygen 17 alpha gamma seems to be much smaller than what you were thinking, and oxygen 17 alpha N much larger than what we were thinking before. So I don't think that, for me, neon 22 alpha N and neon 22 alpha gamma should be the first measurements that need to be done. But yeah, no, I'm not sure. I'm not sure you can get, if the reaction rate is too low, I mean, it would be hard to measure at these energies of interest, I would say. You see, Matt Williams performed the oxygen 17 alpha gamma up to the state here. Where is it? You just get upper limits here for this one. So yeah, I think getting these ones will be hard at these low energies, even for the alpha gamma. I think what you should do is just evaluate what is the yield that you will get with the new reaction rate, with the new cross section, and see if it's manageable or not.
Okay, so let's thank again Peruz for the nice talk. And